Welcome everybody for attending this this webinar, Discover the Benefits of the AIMMS Met Program Inspector. My name is Peter Nieuwstegen and I will be presenting this workshop. So a quick overview of the agenda. I'll start with an introduction. Then I will start with the Met Program Inspector, the main views, how do you navigate through it, and then I end with action menus to do specific action, mainly focused on infeasibility, unboundedness, and just strange solutions, but tools that will help you to make models, to build better models faster, because that's the purpose of this webinar. Things that you can help you during model building, if your model is infeasible or unbounded, to quickly get you to a solution. Or to identify the problem. There will be a few, there will of course be a presentation, there will be a few interactive polls, but there will also be demonstration. And there will be an opportunity to ask questions at the end of the presentation. So let's start with a quick webinar. How often have you used the Met Program Inspector? There's three options: regularly, rarely, and never.
Okay, I've launched the poll. It's not a difficult question, I think, so I think 10-15 seconds will do. Okay, I will close it down. Everyone voted, I think. Okay, and I will share the results. Well, 1/3 regularly and 2/3 are rarely use it, Peter. So.
Okay, so that's good. Then hopefully they will, they will enjoy what they see and learn a lot. So the first thing is the Met Program Inspector views. But before I start that, a little bit about the Met Program. As I mentioned, it's a graphical tool to analyze optimization models. It only works for linear models, mixed integer, nonlinear, mixed integer, nonlinear. It doesn't work for the complementarity problems and the constraint programming problems. Main reason is that they are completely different technology, completely different representations of the model. So today we'll focus mainly on the problem that I will be showing is mainly a linear program, but the same things. It works the same for linear and nonlinear problems. So when you open the Met Program Inspector, this is what you see. And in the screen area, you basically see three different areas. One area is a set of variables. So all variables that you have in your model will be listed in this section. Then there will be the second part will be all constraints. The all individual constraint will be in that part of the model, or in that part of the Met Program Inspector. And in the big area you will see multiple tabs with detailed information, and that information is depending on the selection that you make in the other three. So if you select one constraint on the left side and one variable on the left side, then what you see in the green area is just for that constraint. Now, so there are multiple tabs. There's the Met Program Solution, there's a view, there's some statistical, and actually the solution. And as I mentioned before, what you see in that area depends on what you select on the left side of the window. So what is on the Met Program Solution tab? On the Met Program Solution tab, you basically see, what is the model type? In this case, I'm solving a MIP, the objective, and the status. So you can see, okay, do I have a normal solution? Do I have a unique solution? And even is it up to date? Because sometimes you can make changes in the Met Program Inspector, and then you have to resolve it to actually get the solution. The main purpose of that is to check the model status. Is it feasible? The next part is the matrix view. And the matrix view is basically, a general representation, a graphical representation of the model. What you see here, you see when there's a block, means that there are non-zeros, means that this particular variable is related, or this particular constraint contains this particular variable. Those two variables are in that constraint. You can see that on a symbolic level, that is what you see here, and you can see it on an individual level, like every individual variable. So, for element 1, 2, 3, 4, 5, all elements in the set, you will see, one block. And I will show that in a little bit as well. Now you see here a little bit coloring, and the coloring means the red. If it's really red, that means that the coefficient, the maximum coefficient, is large or very small, meaning it's larger than 1,000 or smaller than 1,000. And the reason is that if numbers are small or large, that might be potential scaling issues. So this is a way to find out, hey, where are my potential challenges? The second part is the matrix statistics. What you see there is the number of variables and a constraint that you have selected in the two left tree, in the two left trees on the left side. The smallest coefficient, the largest coefficient, and it's an easy way of finding out where your model size is. By selecting just one or two constraints, you can see, hey, how many non-zeros do I have in this particular part of the matrix? So you can run step by step through the matrix. Again, mainly for model sizing and model scaling, because you can see here also the largest and the smallest coefficient and the ratio between. So you get an idea, hey, do I have very large numbers and very small numbers in that same part, in that one part of the matrix. The variable statistics. The variable statistics are basically give you information on a particular variable, the number of individual variables, the number of symbolic variables. Symbolic variables is basically the identifiers that you declare. In this case, you see 9, but the actual number of variables is 12,000. Same thing with, okay, how many coefficients do we have in that part for that selected variable? The associated number of matrix elements. Sorry, that's it. And number of constraints. How many constraints is it actually in there? And also information on the solution. How many are non-zero? How many are the upper bound, lower bound, non-basic, basic variables? So you get a high-level overview of the solution from a variables perspective. Now, if you go and select a single variable, meaning not just a symbolic variable or for a whole index, but for one particular element, then it shows a little bit more information. It shows actually what is the variable type. Is it a binary, an integer, a non-negative? What is the lower bound, the upper bound, the actual value, the reduced cost, and also in which constraint it was present. So you don't only see the variables, but you also see the constraints in which it was present. The constraint statistic is very similar, except that now you see it for a particular constraint and not for a particular variable. So it shows a little bit, binding constraint, non-basic constraint, basic constraint, and different types of constraints. And again, if you select a single constraint, you get the constraint type, the right-hand side, the level value. But then it will also show you the definition of the constraint. So you can actually see, okay, what is that constraint in terms of symbolic, what you basically wrote, and how is it in your model with your coefficient, the actual value, and then the primal contribution. And then so you can actually verify, okay, what happens in this particular constraint. Then there's also two tabs with the variables. There's a tab with the variable solution, and the variable solution will actually contain, the level value, or sorry, the lower bound. What is the actual value of that variable? The upper bound, the marginal, what a status is it at bound or between bounds? So this is a way of actually checking the solution to actually see, okay, what is the solution for all the variables or for just a subset of the variables? Because as I mentioned before, what you see in this screen depends on what you see, is determined by what you selected in the right or on the left-hand side. The same is true for the constraint solution. You can see, level value, the bound, the basis status, the bound status. And the purpose is basically to check the actual solution. Before we go to this, so the question is, if you want to determine the number of non-zeros for a particular variable, which of the steps would you be looking at? Would you be looking at the matrix view, the matrix statistics, the variable statistics, or the constraint statistics?
Okay, I will launch the poll now. So votes are coming in. We'll wait a little bit longer. Not everyone has voted yet. And I'm going to close it down. It's closed. I'll share the results, and everyone chose for the variable statistics.
Okay, good. Yes, because because basically with the variable statistics is where you can see it for one particular variable. With the matrix view and the matrix statistics, you can see it for the selected variable and the selected constraint. So not just for the variable. So now it's time for the first demo. But before I go to demo, let me explain the model that I'm going to use. So this is it's a very basic model. You have two farms, and on every farm you have to decide what you're going to do. How much land you devote to keeping cattle, because cattle feed off crops, so you need to make sure that you grow enough land for a particular crop. The amount of land to rent, maybe you want to rent some extra land to grow some more crops. How much you're going to transport between farms, and as you can imagine, and all those cost money or generates revenue, and the goal is to maximize the profit. So how would you now use the MET program inspector? Is that you start AIMMS, you solve your model. In this case, I just solve the base model, and I can see it's nice and optimal. And then I go to the tools menu, diagnostic tools, and then the MET program inspector. And here you see all the tabs that I mentioned. So let me start with the matrix view. In the matrix view, as I mentioned, you have the symbolic representation. So you have here, the variable here is move crop and the crop on hand. So you can see precisely, okay, what this constraint, is. Where there's a block, there's basically, there's non-zeros, and it shows you how many. You see here, there's 2 non-zeros. Here you see there's 2 non-zeros. This is what we call the symbolic view, because it's basically on the basis of a symbolic identifier. As you can see, if I make a selection here on the left-hand side, it will impact what I see here. So now I will see just one constraint and one variable. Of course, on the symbolic level, that might not be. That might not provide much detailed information. So I also have the ability, I have the ability to zoom, because you see here, it didn't show everything. I also have to go to an individual view. So now I see an individual view. So I can precisely see, okay, for this particular constraint, where the variables are. If I now show a selected constraint, I can actually see precisely, okay, what are the variables that are in these constraints. So for this particular land constraint, I see, okay, no, those variables are for that constraint and those variables are for that constraint. And that can be a first way of, of looking at your model. And as I mentioned before, this is where you would look to find missing relationships. Hey, I'm expecting these variables to be this variable and this constraint to be related. Why is that missing? So now, of course, I can also go back to the symbolic view and even to the complete matrix again, as a way of showing, okay, this is what I want to start, so I can see that again. If I now go and look at a particular constraint, and I double-click on that constraint, I can actually, as I mentioned, you will see here the definition, and you see, the number of individual constraints, how many constraints there actually are, and how many non-zeros there are. So other tabs that I often, so this is a tab, the constraint statistic, the variable statistics are tabs that are often looked at because they provide, they'll provide good information. The matrix statistics as well, especially if I look at model size. Because what I often do is like, I select all variables, and then I said, okay, I walk one by one through the constraint, so I can see, okay, this has 20 non-zeros, this has 2 non-zeros, 8 non-zeros, 2 non-zeros, 17 non-zeros. And in that way, I can actually see, especially if I have, if my model is much larger than what I would expect it to be, then I will look at that to say, hey, where are my non-zeros? Which constraint contains the non-zeros? Or in some cases, I look at variable-wise. I say, okay, which variables contain the non-zeros? But these are easy ways to look at. Easy ways to look at, your model size, or scaling issues. If the coefficient ratio is really large, and here it's, it's pretty nice. This is probably the, the largest. Then I might that if I'm looking at numerical issues, then that is also very something that I often do. So that's mostly what about the different tabs. But in the Met program, there's a lot of, in the Met program inspector, there's a lot of features that you can use to navigate to these trees. As I mentioned, if I select this, you see this constraint. But then there are here the next leaf node, the previous leaf node, and that it's also here in the menu, next and previous. It allows you to actually, look to the lowest level, the individual identifier. So you see here in this model, you see every index has its own level. Of course, this is a very small model. Your model probably doesn't have 2 elements in the set. Your probably model has more like 200 or 2,000 or maybe even 20 or 200,000 elements. So in that case, looking at this, it's a little different. Because here you can open everything and it fits all in one screen. But with the next leaf node, the previous leaf node, you can actually, work through the different identifiers and see the value. So what you see here as well is that if you look at this, so here you have the actual variables, the coefficient, and the value. And here is basically the primal contribution is the multiplication of the coefficient and the variable. And if you sum these, you actually get the level value of the constraint. So you can actually see, okay, the value is 100 here. How do you get to that? Well, that's basically 80 comes from this, and 19 or 81 comes from this, and 19 comes from that. So basically the next and the previous leaf node is one way of navigating. Sometimes you say, I want to bookmark. I want to remember which constraints I'm looking at. In that case, you can bookmark it, or you can bookmark a particular variable in the same way. And once you bookmark it, it will highlight, it will mark that constraint blue, as well as all the ones above it. So you can actually see, okay, even if you close your tree, you can still see, okay, there is one. If I now open it, I can see which one it is. So the bookmarking, you can do it in 3 ways. You can do that through that item, or you can do it via this menu, or also via the bookmark menu. But even more powerful is the ability to say associated variables. What that does, it will mark all the variables that are used in this constraint. So in this case, you see feed cattle, grow crops, land rent. So those are the 3 constraints that are mentioned here. And as you can see, precisely the ones related to farm 2. And then you can use the next bookmarks and the previous bookmarks to actually walk through all of them. So you can see, okay, what are all these variables? What are all the constraints that are present? And then if you find a variable that you find, hey, let me investigate that further, you can go back and say what constraints is that used in. And if you're analyzing your problem, that combination is actually very useful, because then it will allow you to, to go back to, okay, this constraint, this variable, where is it used? So you can follow the relationship between the variables and the constraint in a very easy and interactive way. So when I'm analyzing a problem in infeasibility and unexpected solution, I very often use that combination with associated variables in combination with the walkthrough previous and the next. So What are other things that you can do in the, for navigation to look at the data? Sometimes you say, okay, I want to see this constraint and I want to actually go to the attribute window. So what is actually the definition in that constraint? What is the property? What did I write there? Maybe I wrote a comment that I want to look at. So you can do that as well through the attribute window. Another one thing that you can do is actually look at the data. If you look at the data, when you click here, it will actually look at the data for a particular element, for a particular variable that you selected. So here you see, okay, it's for one of the farms. Or if you do it here, it will actually show for the whole identifier. So that's a way of going to the model. Of course, when you do that, when you do the data, you actually see the data on the model that was solved. So because sometimes what you can do is you can say, okay, I'm gonna toggle active. I'm going to deactivate a particular constraint. So in this case now I have deactivated this constraint. If I now solve, my model becomes unbounded most likely. This shouldn't have, it's a little bit too much by oh, I didn't want to toggle active. I want to just toggle active that one. The model is still feasible, it just becomes a little, the objective becomes a little higher because it takes away some restrictions. Now the data that I have in the Met Program Inspector that I show here is different than what I would have shown. Because as you can see here, it's 63 and 32. If I now do data, those values are different because those are the values that were from the model that are originally solved and not from the one that I solved in the Met program. So sometimes when you do those changes in the Met program, you can actually, you can change the model. So things that you can do is you can say, okay, I can deactivate a constraint or activate a constraint. But I also can say, okay, so what is the value here? Solution value 160. You say, well, I might want to change the upper bound to 100 and see what happens. So I click on 100 and then I resolve. As I can see, I see my objective. I see my objective changing and I see this variable changing. So you can change the the type, the lower bound, the upper bound. Those are the things you can change. You can also change the coefficients here in the matrix. Say, I want this to change, and then we'll see here. We see it, the matrix is out of date. I solve it, it's up to date, and I get a new objective. Of course, this is all in the Met Program Inspector. All these changes that I made are in the Met Program Inspector and do not affect the results of the model. And if I close the Met Program Inspector, they're all gone. But it's a good way of analyzing your model. So I want to do a quick review of what we just saw. We saw some of the navigation features that will allow you to navigate to the tree, the next and the previous leaf node, the buttons to say, okay, can we go to the next or the previous leaf node in the tree. an actual variable, an extra constraint, how to bookmark a variable and a constraint, how to walk through those, look at associated variables, associated constraints, the AIMMS attribute window, the data page to actually look at the model, to look at the data in the model, and the change domain index display order. I didn't show that, but I will show that in a bit. Let me go back to model, I forgot. So here you see, you know, as I mentioned, every index on one level. You might say, well, I want to see it. I want to see this ordered by, you know, by crop type. So in that case, what you do, you go to the properties, and here basically says, okay, from to crop type. If you now modify that, you can say, okay, I want to do crop type. Then you would have the crop type first as the first index, and then those two as the next. And then maybe you say, okay, well, I just want them on one level. So in that case, you see, you know, the two crop types, and then you see all these other variables below that. And that's a, you know, that's a way of rearranging the model and the way it looks and the way you can navigate through. And it might be easier to look at it in this way for your particular analysis. And then, as I mentioned, next to the navigation, you also have the ability to toggle active, so to turn off a constraint or a variable. And basically, I don't want this in the model. Can you resolve what happens? So these are the basic navigations. So we've seen the tabs, the navigations, and then the next step is some action menus. And there's a number of action menu. There's an action menu and has a number of items. We already saw the resolve. We saw the associated variables and associated constraints. But there is also ability to calculate an IIS, the substructure causing unboundedness, substructure causing infeasibility, and I will go a little bit more in detail because these are very key in finding out problems in your model. And then there's bound analysis and unbounded variables in constraint listing. So the resolve, we already saw that. You can resolve a model after changes like a toggle active or when we make a bound adjustment. Like if I change, or when we change the coefficient, by resolving you can actually solve the model again. We saw the associated variables and constraint, but basically they highlight the associated variables highlight the variables present in the selected constraint. And the same thing for the associated constraint. You highlight a constraint containing the selected variable. A bound analysis is actually a useful tool because it calculates implied constraint and variable bounds. So you can imagine that sometimes you have, you have certain constraints, certain variables that will have bounds, and basically based on the bounds of that, based on the bounds of the variable, you might be able to adjust the bounds of the constraint. And that is actually a very good step in detecting infeasibility, because once you try that, and then the solver or the MET program inspector will say, okay, all these bounds can be reduced to something that's infeasible, then it's actually very clear which bound reductions it did, and also which constraint is infeasible. Then there's unbounded variables that will bookmark variables that have either an inf or a min-inf or inf as at least one of their bounds. It's a useful when you have an unbounded model, because of course a variable has to be unbounded in order for the model to become unbounded. So that's a good menu when you're looking at infeasibility and at unboundedness. And then there's the unreferenced identifiers, and that's a way of for AIMMS to tell you, well, maybe you've forgotten this. As you know, you can have different variables, different constraints set in your model, and it will link constraints that are, it marks variables constraints that are not in your model set while they actually contain reference in the variables and constraints that are present. So if you have a constraint containing variables A and B, constraint A is in your model, but variable A is in your model, but variable B not, then AIMMS will list the B as an unreferenced identifier, because it says, hey, maybe you should have that in your model as well. So these are useful menus that you will use regularly. But the main one that I often use is the MIP structure causing infeasibility. And the purpose is actually to get more insight on why a model is infeasible. And basically what it does underneath, it adds a slack, violation variable, slack variable, to all variables and constraint bounds, which basically means that at that point your model is no longer infeasible because every constraint becomes a soft constraint. There's a few exceptions, variables by the definition. The reason is that you want the definition also to be true, because if you're not, then you change the model. So by default, you don't add slack variables there. 0 variable bounds in general are hard because they are very physical, and the bounds on binary variables or they normally don't make sense to be non-binary. So they will be hard constraints still. And then you can actually change that. It's a default. You can say, okay, I don't want to slack on this constraint or this variable. AIMMS will then solve, or the Met Program Inspector will solve the adapted model with all those slack variables, trying to minimize the slack. And all variables and constraints with non-zero slack in the optimal solution will be bookmarked. So at that point, you'll have a set of variables or set of constraints that will make the model infeasible, or where if you relax it, you can make the model feasible. So that's one way of looking at infeasibility to help you, and I will give a demonstration how that would be useful. The second one is using is to calculate an IIS, and an IIS is basically a minimal subset of constraints and variable bounds that contains an infeasibility. So the way that AIMMS calculates the IIS, or the Met Program Inspector calculate the IIS, is basically it starts the same way as the previous model. It solves an elastic model, meaning it adds slack variables to everything, and then it has some logic in there to find a minimal set. If you're more interested in precisely how that is calculated, there's a reference at the end of my presentation containing the detailed way of how that is calculating. So you have two ways of finding infeasibility, the substructure causing infeasibility or the IIS. In general, the substructure causing infeasibility is faster because it just needs to solve that one model with all those bounds. On the other hand, the IIS returns a smaller subset of the constraint. So it's a trade-off between fast or small. What I normally do is I try to start with a substructure causing infeasibility because that's a quicker way. If that doesn't help, then I turn off the ability to violate some variables and constraint, that think, I don't think this is the problem. And then I solve the model again and see, or try to calculate the substructure causing infeasibility again, and try if I can find the solution in that way. If that doesn't work, then I try the IIS. The disadvantage of the IIS is that it just takes a long time. Of course, for the small problem that I'm demonstrating, it's not that hard, but for a large problem, it can take up a significant amount of time. So that's two tools that you have to solve infeasibility. There's also one that's unboundedness. That basically works as follows. What it happens, the Met Program Inspector will add a large M to all infinite bound, either inf or minus inf, which means at this point your problem will become fully bounded. It solves that model with bounded, with all the variables bounded, and it will mark the variables in constraints that that basically reach that large bound, because those are the ones that are actually, you can imagine that if the bound is larger, and then it will still continue to be large, and those are the ones that are causing your problem. And this technique is described, that the Met Program Inspector uses, is described in the book of Bruce McCall, from which also the example came that I'm demonstrating. So let me show how that works. So now let me solve a model that I know is infeasible. It changes the model a little bit. As you can see, it's infeasible or unbounded. I open the Met Program Inspector, and then the first thing that I do in the action menu, so I still have to decide whether or not it's unbounded or infeasible, because in this case the pre-solver determined. So what I always do then in that case, I do substructure causing unboundedness. Then basically says, the Met Program Inspector say, okay, the model seems to be infeasible, not unbounded. So the problem is that I have an infeasible model and not an unbounded model. So then what I do is I do as I said, I select substructure causing infeasibility. Now AIMMS marks one constraint as being the problem. So what you can see here is the feed kettle, it says the value to be 30, while the right hand side is actually 50. So there's here total infeasibility is 20. So basically what this means is, okay, the model says the variable should be 50, but the only feasible solution is to be 30. So what I now remember is, okay, we know that, okay, let's see what happens if the feed kettle becomes 50. So what I do now is I say, okay, I make this constraint hard. So I go to the properties, and then I remove this, the violation. So meaning that at this point, it can't violate that constraint. I resolve the model, see it's still infeasible or unbounded. I know it's infeasible. And I do a substructure causing infeasibility. Okay, the next constraint is the rental land from farm 1. It says, okay, land rent should be smaller than rent available. Here it wants the value to be 400. The right hand side is actually only be 200, so that's where you can see it solves the model with a violation. Again, same procedure. Okay, let me say I don't want to violate this constraint, make that a hard constraint. So now we basically have two hard constraints. The feed kettle should be at least 50, and the land rent should be smaller than 200. I solve the model. It's infeasible, of course. Substructure causing infeasibility. And now I see, okay, it marks this constraint. Okay, so what does it mean? So feed kettle was at least 50. So which means that, okay, the coefficient is 10. 10 times 50 is 500. Let's say we don't do any crop. The maximum land rent is 200, which implies that, you know, the land available should be at least 300. Oh, but here we see that the land available is just 100. Okay, so that combination is what making the model infeasible. Now, why would that be? That of course depends a little bit on, you know, the problem. You know, what would be why is this model infeasible? Is that because, you know, the land rent should be more, you should have more available land rent, or maybe the feed, you know, the cattle doesn't need as much land than what you have here. But at least that is a way of finding out, you know, where is the infeasibility by saying, okay, I want to make this constraint hard. You know, as I said, I made the minimum cattle constraint hard, and the land constraint I made hard. And in this way, I found out, you know, where the problem is. So I can also do an unbounded model. I open the Met Program Inspector. I go Substructure causing unboundedness, and you can see, okay, it marks a lot of identifiers, but they all are related to farm 1, as you can see. Now, if I want to say, okay, the variable solution is now a very useful tool, because I can actually sort them by value, and I can see which one are the large one. I see, okay, the feed cattle is a very large number, and the land rent is a very large number. So basically, what the model says, okay, the model is infeasible because you're just gonna, you know, grow an infinite amount of feed cattle, which requires an infinite amount of land to rent. But that's how you make an infinite amount of money. Well, you probably say, well, no, you probably can't rent a limited amount of land. So there should be a constraint on this number, land rent, that shouldn't be as high. But basically, by you can find it out by having the substructure causing unboundedness. AIMMS will point you in the right direction of which model or which variable is going to reach its upper bound. Another poll. Your model is infeasible. What is the first menu that you would try? Would you try the IAS, the substructure causing infeasibility, the bound analysis, the unbounded variables, the constraint listing?
Okay, I've launched the poll. Votes are coming in. I think almost everyone has voted now. We'll wait a few seconds for the last few votes. Okay, and I'm closing the poll and will show the results. Everyone chose for substructure causing infeasibility.
It's a little mean. I was a little mean here because that's actually what I demonstrated. Yeah, so of course, you wouldn't do constraint listing. That's not very helpful. Same thing with unbounded variables. That doesn't help you with infeasibility. The IAS would be possible. It's just not as good. As I mentioned, start always with the substructure causing infeasibility. But before you do that, just try bound analysis, because bound analysis is actually a very simple way that can actually help you. Much easier. And let me demonstrate it in this model. Let's say I'm solving the infeasible model again. Met program inspector, and then I do bound analysis. It basically says, okay, the lower bound of feed cattle is tied can be tied from 0 to 50. The land rent goes to 200, and then the problem is in constraint land, because that causes infeasibility due to the associated variable bound. So here you know precisely that, okay, this variable is causing the problem, this constraint is causing the problem. In combination with these bound reductions, you know exactly what the problem is. So my poll was a little mean because that's not what I didn't tell you that. So what you've seen in this webinar is basically the view tabs to see detailed information on the selected variables and/or constraint. You see how you can navigate through your constraint and variable tree with associated variables, next bookmark constraint, previous ones, and some action menus to help you find infeasibility or unboundedness. As normal, we'll make the material that we shared, we'll make the slides available, but here you have some reference to that can help you in finding if you want to know more about infeasibility or unboundedness. The next webinar will be next month on June 17, in which my colleague Ovidio Listis will present the webinar with the title Network Optimization Using AIMMS in the Analytics and Visualization area. And again, this will be held on the same times. At the end of the webinar, we'll ask you for some feedback. What did you think of the webinar? And if you have any suggestions for future topics, we're always looking to see, what would people be interested in to learn more in a webinar.